Science fiction makes a casual habit of distance. A sentence, a dissolve, and a crew is already at Saturn. We recognize the soundstage shorthand warp flashes, stars smeared to lines, and we accept it because story runs on compression. But our solar system does not. It is not a neighborhood. It is a desert. The nearest oasis, Mars, drifts anywhere from tens to hundreds of millions of kilometers away. Across such emptiness, our technology does not leap. It grinds, conserving momentum the way a weary traveler rations water. All rocketry begins with a bargain that nature will honor without mercy. If you want to go one way, you must throw something the other. Momentum is conserved always, exactly. In a chemical rocket, we cheat a little by making the something very hot very fast. Oxidizer meets fuel, atoms rearrange, and the exhaust is flung rearward at high speed. The rocket's nose nudges forward in equal measure. It's the same principle that sends a punctured balloon screaming around the room, only refined to the edge of metallurgy and math. There is a romance to this, the first cough of ignition. The bellowing plume, but hidden in the spectacle, is a quiet limit. The speed of that exhaust, the effective velocity we can give our escaping gases with chemical energy, tops out. You can empty bigger tanks, stack more stages, invent cleverer pumps, but the physics of chemical bonds draws a line through your dreams. Faster travel by the same means mostly means carrying more propellant, which makes you heavier, which means carrying more propellant. The snake swallows its tail. We've seen this spiral written in steel. Consider a modern moon booster, a skyscraper of tanks that empties almost before you can describe it. Millions of liters of cryogenic propellants gone in the first 10 minutes. A magnificent extravagance, and a sign that brute force is a poor currency when the bill is measured in interplanetary months. If you tried to accelerate all the way to Mars, and then decelerate for arrival using only chemical engines, your ship would become a flying fuel depot, too vast to launch and too hungry to sustain. The equation behind this predicament is older than any launch pad. Tsiolkovsky gave it to us in the 19th century. The change in a rocket's velocity depends on the exhaust velocity and the ratio between the rocket's full mass and its empty mass. That ratio grows cruelly fast as you demand more delta V. Stack stages to tame it and you inherit complexity, accept longer coasting arcs and you inherit time. Chemical propulsion, by its nature, pays for speed with propellant and pays for propellant with still more propellant. This is why agencies speak in months, not days. A 7-month cruise to Mars isn't a lack of ambition, it's an act of restraint. The trick is to burn hard only when you must at launch, to claw free of Earth's gravity, at arrival to be captured by the destination and coast in between, husbanding the fuel that remains. Our rockets fly like prudent captains in a wooden age, reading the winds, conserving their casks, knowing that waste at the start becomes hunger at the end. That prudence comes with costs beyond the calendar. Time in transit is risk, to radiation, to equipment failures, to the open-ended boredom that can pry open the human mind. Time in transit is also mass, because the supplies you pack for a long voyage are part of the same tyranny that dictates your tanks. Every day saved is kilograms not launched, dollars not spent, margins gained for science instead of survival. Speed is not a luxury in space. It is a kind of safety. So we search for ways to change the bargain. Momentum will still be conserved, nature will see to that, but perhaps we can choose smarter how we pay it. In the simple algebra of thrust, momentum is mass times velocity. Chemical rockets pay by throwing a lot of mass moderately fast. What if we throw a little mass very fast? If the stuff we hurl rearward leaves at tens of kilometers per second instead of just a few, then the same momentum can be bought with a fraction of the propellant. The rocket grows lighter. The spiral slackens. To do that, we must step away from fire and into fields. Electric propulsion does not ignite. It accelerates. It takes atoms or molecules, strips electrons, and then uses electric and magnetic fields to fling the resulting ions out the back. Where chemistry sets the ceiling with energy stored in bonds, electricity lets us spend power collected from elsewhere solar arrays. reactors to pump up exhaust velocity as high as our circuits, grids, and magnets can bear. The push at any moment is gentle, sometimes laughably so, but it never needs to stop, and in the vacuum where nothing fights you, a whisper given hours becomes a wind. Before we touch that future, we should admit the temptation to pretend it has already arrived. Science fiction hands us drives with names like Promises Warp, Hyper, Epstein, and by naming, skips the proving. The real machines on real spacecraft are humbler and more stubborn. They sputter at first, they erode, they ask for rare gases and more power than our panels can spare. They remind us that progress is not a montage but a workshop, and that the solar system will open to us only at the pace we can solve its equations. Still, the key is in the lock. We can see the outline of a solar system where months shrink to weeks and years to months, not because we learn to ignore conservation of momentum, but because we learn to spend it differently. We will still throw mass overboard to go forward. We always will. The question is whether we can afford to throw far less of it, far faster. For that, we turn to engines that hum instead of raw plasma lit by electricity, ions steered by fields, exhaust as thin as a whisper, and as relentless as time. We turn, in other words, to a different way of leaving home. Imagine taking the breath that powers a balloon and teaching it patience. No blast, no thunderclap of ignition, just a steady exhale, hour after hour, day after day, until the quiet becomes irresistible. That is the spirit of electric propulsion. Where chemical rockets gamble on heat and haste, ion engines wager on time. They exchange torrents of propellant for a trickle accelerated to astonishing speed, and in the frictionless dark that separates worlds, that trickle accumulates into destiny. The physics is the same oath every rocket swears: momentum must balance. Chemical rockets buy their forward motion by hurling enormous amounts of exhaust rearward at a few kilometers per second. Ion engines buy the same momentum differently. They start with a neutral gas, xenon is the favorite, because it is heavy, inert, and easy to ionize, and they strip away electrons to make positively charged ions. Electric grids or magnetic fields seize those ions and fling them out of the engine at velocities chemistry can only envy. Depending on design, the exhaust can scream away at speeds that translate to roughly 146,000 kilometers per hour. The rocket, by Newton's book, nudges forward. The magic here isn't mystery, it's math. Momentum is mass times velocity. If you can make the velocity term enormous, the mass term can be very small. Compared to the wasteful appetite of combustion, this is thrift of a radical kind. You carry less propellant. You spend it slowly. You accelerate not in a sprint but in a vigil, and because nothing rubs against you in vacuum, that vigilance pays back with interest. A spacecraft that sips propellant can thrust for months, for years, curving its trajectory with a hand so light the stars themselves barely notice. This is why people who build missions talk about specific impulse like it's a love language. Chemical engines do splendid work for a few minutes. Their efficiency in turning stored chemical energy into thrust might reach a few dozen %. Ion engines, by sidestepping flame and tapping electrical power to accelerate propellant directly, can push their efficiencies much higher numbers that, in engineering reports, make planners dream. You can hear the consequences in the way mission design changes. Instead of massive tanks that empty in their first act, you get slender propellant budgets stretched across entire voyages. Instead of choosing between payload and margin, you can sometimes have both. And this isn't an untested fantasy. Electric propulsion has already threaded itself quietly through the history of spaceflight. When Deep Space One went comet hunting at the turn of the millennium, its N-Star ion engine was more than a propulsive experiment. It was a proof that the patient push could guide a craft across the inner solar system. Years earlier, Hall effect thrusters were already keeping Soviet satellites trim, using a torus of electrons to trap and accelerate ions in a compact geometry that made station keeping practical. Today, when you look up at a clear night and imagine the shoal of SpaceX Starlink satellites circling Earth, many of those small, flat-bodied birds are breathing xenon, or krypton, through Hall thrusters to raise or tweak their orbits. Even large structures have tested the idea. China's Tiangong space station uses chemical propellant for the heavy work, but has flown Hall thrusters to help with precise orbit maintenance, a rehearsal for a future in which giant platforms tend their trajectories with electric grace. Yet every yes from electric propulsion comes tied to a stubborn but. The but is thrust. If you were to hold your hand against the plume of a typical ion engine, the push might feel like the weight of a sheet of paper. That is not a metaphor designed to impress a launch pad. Ion engines are magnificent at turning electricity into high-velocity exhaust. They are terrible at producing large forces in a hurry. They cannot lift a vehicle from Earth. They cannot yank a crewed capsule out of danger in the first 2 minutes after liftoff. Their gift blooms only after a chemical booster has paid the price to reach orbit. Up there above the weather, above drag, above the tyranny of air, they begin their sermon in whispers. Give them days, and the whispers shape a wake. Give them months, and a probe can outrun the shuttle's peak by a factor of 10 or more. But if you ask them for a shove right now, they demur. The gentleness isn't a flaw. It's a design choice, forced by the very efficiency we covet. To keep specific impulse high, you hurl tiny mass very fast. To hurl more mass without squandering efficiency, you need more electric power. In deep space, power comes from solar arrays or reactors, and both have limits. Panels grow large and delicate. Reactors are heavy and politically fraught. The upper cap on these engines, for now, isn't how much propellant you can stuff in a tank, but how many electrons you can marshal to accelerate it, and how long your components can endure the electric storm you've created. Endurance is not trivial. Electric thrusters are circuits as much as engines, a choreography of electrons and ions. Stray charges, whether from space weather or from your own plume, can skew the fields that keep the dance in time. Grid erosion gnaws at gridded ion thrusters. Sputtering slowly eats the parts that must shape and accelerate the plasma. Hall thrusters trade grids for magnetic traps and wear differently, but they too must make peace with the slow sandblasting of their own exhaust. Engineers have answered with better materials, clever cathodes, and field geometries tuned like instruments. But where is a tax that must be paid in design and power margin? Then there's the simple matter of what you feed the thing. Xenon is popular because it's dense and docile, but it is also rare on Earth, and not cheap numbers on the order of $1,000 per kilogram hover in procurement spreadsheets. For a handful of satellites, that is acceptable. For an economy of tugs, transports, and station keepers, it becomes a line item that shapes strategies. Could you use argon? Vastly cheaper and more abundant. Many Hall thrusters can, with some performance penalty. Could you sip the thin breath of Earth's upper atmosphere to maintain a very low orbit, harvesting your own propellant on the fly? Concepts exist, and early tests have teased the possibility, but the practical hardware is still a work in progress. Even at their best, the personalities of these engines demand a new rhythm for missions. Picture a probe leaving Earth. A chemical stage tears it from the pad. Another lights to push it beyond the last wisps of air. And then, in the hush of orbit, the electric engine wakes. The thrust is so small you could deny it's there. Yet onboard accelerometers know. Navigation teams on Earth know, because the trajectory bends in ways the math predicts. After 2 days, perhaps the craft has only the speed of a car on a highway to show for it. After 2 weeks, it has the speed of a supersonic jet. After 2 months, the accumulated delta-V eclipses what a chemical upper stage could have afforded the payload. The engine is still breathing. The propellant tanks are far from empty. The mission profile that looked timid at launch now begins to look bold. The implication is subtle and thrilling. You trade drama for reach. No single thunderous burn, no single cinematic moment, only a string of tiny accelerations that, integrated over time, become strategy. For station keeping and orbit raising, that strategy is already standard practice. For deep space science, it is becoming an art. For cargo ferries to Mars, asteroid miners, and robotic scouts, meant to crisscross the sun's domain cheaply and often, it may be the difference between a few spectacular one-offs and a civilization that travels as a matter of course. There are, as always, frontiers within the frontier. Some of the limitations of today's engines' thrust levels, propellant choices, erosion are being pushed outward by new architectures and materials. Others collide with wider systemic questions. How much power can you realistically carry? How do you reject waste heat when your power system scales up? Where will your propellant come from in a solar system where launch costs still dominate every budget? Those are questions for the next chapter, where experimental plasmas, variable specific impulse, and hungry megawatts promise to turn gentle into swift, without giving up the thrift that makes it all worthwhile. For now, we can say this much without blushing. Ion engines have already changed how we move. They are the quiet motors in our new ships, engines that do not roar but endure. They cannot get us off the ground. They cannot save us in a pinch. But over the long, patient arcs that tie planet to planet, they make a promise no chemical flame can match. Keep me powered, and I will keep going. In the void, persistence is a kind of strength all its own. If today's ion thrusters are the patient monks of propulsion, tomorrow's prototypes are the apprentices in the cloister yard, hands blackened, eyes bright, failing and learning in equal measure. They aim at the same vow-trade propellant mass for exhaust velocity, but they reach for bolder liturgies, hotter plasmas, cleverer field geometries, fuels you can actually afford by the ton. The promise is simple to say and hard to keep. Keep the thrift, add the oomph. Start with helican thrusters, descendants of a deceptively modest idea. Use radio waves to make a better plasma. A helican antenna wraps a neutral gas xenon if you can pay for it. Argon if you can't, with a whirling electromagnetic field that strips electrons more efficiently than a hot filament can. Downstream, a drop in electric potential, often a naturally forming double layer, acts like a waterfall for ions. They rush through and out, accelerated without slamming into metal grids. Less hardware in the plume means less erosion, and less erosion means an engine that can run not for weeks but for years. The European Space Agency's work with Australian plasma physicists has pushed this concept forward. Higher efficiency at lower wear, the exact trade you want if your mission plan reads like a calendar, not a stopwatch. If a Hall thruster is a robust tugboat, a well-made helican is a glider that never lands. But longevity alone won't move freight between planets. You also need options for what goes in the tank. Xenon is the darling propellant for a reason. It is heavy, inert, and tames easily under electric fields, but it's scarce and expensive on Earth. The next cohort of engines is built to be less picky. Magnetoplasma dynamic thrusters, MPDs, for instance, are brutal in their simplicity. Drive a current through plasma, wrap it in a magnetic field, and let the resulting J times B force hurl the exhaust aft. Because the working fluid is a current-carrying plasma, MPDs can burn what the mission can spare. Hydrogen cracked from water, argon skimmed from an atmosphere, nitrogen or ammonia loaded cheap in bulk. In certain regimes, with the right inlets and at the right altitudes, they can even gulp trace molecules from the tenuous fringe of Earth's air, flying so low that drag would normally kill a satellite, and use that whisper of intake as their own propellant. Imagine station keeping that grazes the stratosphere's ceiling, paying the rent in captured breath instead of trucked xenon. The price you pay moves upstream. Power. An MPD is a creature of amperes. To get useful thrust, you must push serious electrical current through your plasma, which means your spacecraft must be a power plant as much as a payload bus. The same is more true for a machine with the reputation and ambition of VASIMR, the variable specific impulse magnetoplasma rocket. Where a classic gridded thruster is a tidy ion gun, Virginia Simmer is a miniature storm. A first stage turns neutral gas into plasma. A second stage dials radio waves to the cyclotron frequencies that heat ions to astonishing temperatures up around 1,000,000 degrees in the marketing copy, and in lab plasmas, confined by magnetic fields that keep the inferno off the walls. The party trick is in the name. You can trade specific impulse for thrust on the fly, dial the exhaust velocity down and the mass flow up when you want a shove, and then reverse the ratio to sip propellant over a long cruise. In concept, it merges the patience of electric propulsion with bursts of urgency, a ship that can loiter and lunge. It is also, as the engineers will tell you, ravenous. If ion thrusters are bicycles and hall thrusters mopeds, VASIMR wants the freeway and a full tank. The often cited Dream Mars in something like 5 or 6 weeks assumes power levels measured in tens or hundreds of megawatts. That is not a quirk of the engine. It is the bill for asking for both high exhaust velocity and meaningful thrust simultaneously. In the quiet vacuum of space, there is no air to carry heat away, so every watt you spend must be turned into directed exhaust or dumped to the cosmos as light. Giant radiators unfold in the mind's eye, panels and loops, heat pipes and pumped coolant, surfaces tuned to glow their waste away. You can't hide from the Stefan Boltzmann law. Even efficient engines make heat, and at megawatt scales, the radiators that reject it become architecture as consequential as the thruster itself. This is where days, not months, stops being a propulsion problem and becomes a spacecraft problem, and then a civilization problem. Power at the hundreds of kilowatts level is awkward but tractable with modern solar arrays near Earth. Push toward Mars and sunlight softens. The panels balloon, the pointing constraints multiply, the fragility grows. Fission reactors promise steadier wattage in a smaller footprint, but they drag mass and politics in their wake. A fast cargo tug that sprints between Earth and Mars with electric thrust isn't just an engine bolted to a tank. It's an integrated power and thermal system that happens to throw ions for a living. And yet the benefits pile up when you start assembling missions from these parts. If you accept that you'll always need chemical rockets to escape gravity wells quickly, electric propulsion can take almost everything else. Launch a tanker's worth of argon cheaply and sip it over months. Spiral a heavy payload outward from low Earth orbit instead of spending it all in a single burn. Pre-position habitats and life support at Mars orbit, ready to catch a crew that follows later on a more austere transfer. Treat the inner solar system like a set of train routes. Chemical boosters as the engines that shove you onto the main line. Electric haulers as the locomotives that keep the freight flowing, on schedules measured in weeks and months instead of years. The engineering frictions are honest and many. Plume erosion still eats hardware, even in designs that keep metal out of the hottest flow. Magnetic nozzles are elegant but fussy. Cathodes that must emit torrents of electrons can be fragile throats in otherwise robust throats of fireless flame. Argon is cheaper than xenon by some 2 orders of magnitude, but it is lighter and gives less momentum per ion unless you push the velocity higher, which loops you back to power again. Air-breathing concepts face the paradox of their promise. To fly low enough to harvest gas, you invite drag that demands more thrust, which demands more power, which makes you heavier, which invites more drag. Every solution has a tail. Still, the trajectory of the field bends toward usefulness. Helicon sources promise lifetimes that match the patience of their missions. MPDs hold a toolbox for worlds where xenon is a rumor and nitrogen a certainty. VASIMR sketches a future where variable isn't a line in a paper but a knob on a pilot's console. Above all, mission designers are learning to fly with these personalities instead of against them, accept low thrust, and shape spirals instead of darts, accept power hunger, and design for radiators first, instruments second, accept long burns, and write operations plans that unfold like novels rather than heists. As these engines mature, their most important contribution may be psychological. They make the solar system feel knit together by routes and timetables. A freighter of habitat panels leaves cislunar space every synodic window, taking 50 days on the fast lane when the power grid is flush, 80 when it isn't. A tug skims low over Earth's rim, refilling its propellant tanks from the air itself before boosting a telescope to a quiet orbit where it can stare for a decade. None of it looks like the punchy cinema of liftoff. All of it looks like commerce. We are not there yet. The gap between laboratory plasmas and a civilization's logistics is measured in heat exchangers, contracts, and patience. But if you squint at the prototypes, the Helican glow, the MPD's electric thunder, the VASIMR's magnetic cage, you can see the outline of a fleet that moves not by expending everything at once, but by cultivating power and spending it wisely. We will still need fire to leave the ground. Between worlds, though, the engines that hum may be the ones that carry us fastest, because they can keep humming as long as we can keep them fed. To feed them, we will need more than bigger panels. We will need to think at the scale of a star. Every advance in propulsion pulls behind it a shadow, power, ion engines, helican thrusters, VASIMR storms all whisper or roar the same demand. To fling ions faster, to trade patience for urgency, to collapse months into weeks, you must feed the machine electricity in volumes our spacecraft have never known. Where does that power come from? Arrays of solar panels like glittering wings, compact reactors glowing in shadows, or something larger, something that makes today's infrastructure look like campfires against a glacier? It is here that a half-century-old thought experiment, born of physics and science fiction, waits patiently, the Dyson sphere. Not a solid shell encasing the sun, as comic book illustrations like to imagine, but a swarm, a constellation of mirrors, panels, or habitats orbiting the star, drinking in its light and redirecting the flood. Freeman Dyson, in 1960, suggested this not as an engineering plan but as a way to recognize alien industry. A civilization advanced enough to thrive beyond its homeworld would eventually tap its star directly. If we wanted to search the galaxy for neighbors, we should look for stars dimmed or reddened by a shroud of collectors. The irony is that his speculative aliens became a mirror for us, because when you chart humanity's appetite for energy, the line does not slope gently. It curves upward, steep and greedy. We are 8 billion now, drawing down some 4 times 10 circumflex 20 joules a year. Oil and coal still anchor that ledger, but their reserves are finite 150 years at best, fewer if demand keeps climbing. Even if we patched the gap with fission or renewables, the trajectory points toward a hunger far larger. With population growth at even a modest 1% compounded, humanity would number in the tens of trillions within a millennium. At that scale, not even Earth's total sunlight is enough. You either cap your growth, or you step up your source. The sun, of course, radiates with profligacy. At Earth's orbit, every square meter receives about 1,360 joules per second. Multiplied across the disk, our planet cuts through sunlight. That's 1.7 times 10 circumflex, 17 watts pouring past us, day after day. Over a year, it amounts to some 4.7 times 10 circumflex 24 joules, 10,000 times what we burn in fossil fuels now. And that's just the slice that brushes our planet. The sun as a whole radiates 3.8 times 10 circumflex 26 watts, most of it wasted into empty dark. If you could capture even a fraction, your energy problem dissolves. Your propulsion problem too. Suddenly megawatt thrusters are trivial. Radiators are sized by engineering convenience instead of desperation. Voyages shrink by order of magnitude. The mathematics intoxicates because it feels so simple. Imagine mirrors rather than panels, orbiting in swarms, angled to beam light where you need it, onto orbital foundries, into microwave collectors above Earth, onto the radiators of a starship bound for Jupiter. You don't even need to convert all that light into electricity first. You can work in photons directly, shifting them like currents in a grid. And once you place one collector, its power can help build the next and the next, bootstrapping into an exponential curve. Where 425,000 years to disassemble Mercury looks absurd, 31 years with exponential replication looks uncomfortably plausible. Of course, sphere is a misnomer. A rigid shell is impossible, mechanically unstable, absurdly material, hungry, gravitationally disastrous. But a Dyson swarm, a loose collection of orbital satellites, each independent sidesteps those problems. They don't touch, they don't need to. Their combined area is what matters. With enough of them, the sun becomes a power plant. You don't just orbit, you inhabit. This scale of construction belongs on the Kardashev scale, the cosmic yardstick for civilizations. Type I uses the energy of a planet. Type 2, the energy of a star. Type 3, the energy of a galaxy. We are, perhaps at type 0.7, still dependent on dead plants and buried hydrocarbons. To reach type 2 is to stop thinking of energy as a bottleneck at all. It is to imagine colonization as an accounting problem, not a physics one. Ships don't wait for transfer windows. They burn when they choose. Settlements on Mars or Titan don't budget kilowatt hours like lifeboat rations. They flood their domes with power as casually as we plug in a phone. There are, of course, costs measured not in joules but in conscience. A Dyson swarm built from Mercury's bulk would strip a planet bare, leaving a scar where once an entire world circled. Do we grant ourselves that right? Or do we argue that no one lives there, that ethics begins and ends with sentience? Do we build with lunar regolith instead, or with the rubble of asteroids? And how do we reckon with the orbital mechanics of billions of independent panels, each needing station keeping, each subject to the slow tug of planets and the breath of solar wind? The swarm is less a single machine than an ecology, one that must sustain itself over centuries. Yet the logic loops back, again and again, to necessity. Propulsion drives us to power. Power drives us to the star. And once you admit that our own growth will not stop at billions, the Dyson swarm becomes less a fantasy than an inevitability, a line item on the long arc of survival. Perhaps it is a project for 1,000 years. Perhaps it begins in the next century, with a few mirrors in Mercury orbit feeding beamed light to factories on the moon. Perhaps our children's children will look up at the sun and see not a perfect circle, but a patterned shimmer as human industry begins to weave itself across its face. We are not close, but we are not as far as we once were. Solar sails, orbital mirrors, space-based photovoltaics, they are already small rehearsals for the choreography a Dyson swarm demands. Each step teaches us something about attitude control, about beam steering, about managing swarms of machines in orbits that intersect and precess. And in those lessons, the audacity of Dyson's idea begins to shrink from myth to engineering. Because the true lesson of Dyson's sphere is not the geometry, it is the principle that the boundary of human expansion is not set by fuel, but by imagination and will. If we solve propulsion but not power, we drift slowly outward, rationing our journeys. If we solve power as well, the solar system stops being an archipelago and becomes an open sea. And when that day comes, the same sun that now blinds our eyes may instead illuminate a lattice of our own, making a crown not of fire, but of mirrors, each one a stepping stone to a wider home. It begins with a thought experiment, one that sounds almost violent in its simplicity. If you want to build a Dyson swarm, you need material, vast amounts of it. Steel and silicon and composites, not in kilograms but in planetary volumes. Where do you get that? Earth is off limits. Strip mining, the only cradle of life we know, is unthinkable. The moon is closer, but smaller. Its resources shallow compared to the need, which leaves the innermost world, Mercury, rock, metal, and no inhabitants to protest. Mercury is both cursed and blessed for this role. Cursed because its gravity, though weaker than Earth's, still binds its rocks tightly. Blessed because it orbits close to the sun, where sunlight is abundant and power for mining and manufacturing is nearly free. Its surface is rich in metals, iron, nickel, and silicates, and by volume, it might just hold enough to seed an entire swarm. Imagine a future where the planet closest to the sun dwindles, hollowed by human industry, piece by piece transformed into mirrors and collectors that drift outward like pollen in a solar breeze. But this is not simply a matter of digging. Every kilogram you lift from Mercury's well must pay the toll of gravity. To strip the planet into orbit requires not just shovels, but energy, astronomical energy. Physicists sketch this in gravitational binding energy, the price tag of breaking a planet into usable fragments. For Mercury, it's on the order of 2 times 10 circumflex 30 joules. Compare that to the sunlight Earth receives in a year, about 4, 7 times 10 circumflex 24 joules. And the scale of the problem comes clear. Using only Earth's share of sunlight, the disassembly of Mercury would take hundreds of thousands of years. And yet the arithmetic changes once you cheat the curve with replication. One mirror in orbit gathers sunlight. That sunlight powers machines to build 2 more mirrors. 2 build 4, 4 build 8. Exponential growth is the trick of life itself, and applied to engineering it turns geological time into human time. What begins as a 400,000-year slog collapses into a handful of decades. If machines could replicate reliably, if energy could be redirected wisely, Mercury might vanish in a single human lifetime. What sounds absurd as bulk excavation becomes plausible as a self-sustaining cascade. Picture the choreography. Automated miners scoop regolith and ore. Furnaces driven by concentrated solar light refine metals. Automated factories assemble thin film mirrors. Launch systems, perhaps, electromagnetic mass drivers, hurl the panels into orbit without the need for chemical fuel. Each new panel joins the swarm, immediately returning power to the system, feeding the next generation of machines. It is not a single heroic effort, but a colony of machines, reproducing like an ecosystem. Humanity would provide the initial seed, and then watch as the process accelerates beyond any single hand's control. The image is breathtaking and disturbing. To peel apart a world is to commit an act of violence against the solar system itself. Mercury would cease to be a planet and become raw material. Would we justify it by claiming there is no life there to mourn? Would we mourn on its behalf? Planetary ethics is still a young philosophy, and a Dyson swarm would force us to grow it quickly. Perhaps we would first turn to asteroids, nibbling at rubble piles and metallic planetoids, before daring to dismantle something as singular as Mercury. Perhaps we would cloak the effort in language of necessity. Survival requires energy, and energy requires sacrifice. The costs are not only ethical. Engineering would groan under the burden of scale. Launching thousands of mirrors means coordinating their orbits so they do not collide, adjusting for solar wind, correcting for resonances with other planets. Each panel must station keep, must communicate, must know its neighbors. The swarm is not a single structure but a society of machines, billions, maybe trillions strong, and any society that large must deal with failure. Panels will drift, erode, shatter, orbits will decay. Swarm management becomes swarm governance. And yet, the allure remains. A Dyson swarm is not only power for propulsion, it is power for everything. With the sun's energy harnessed, the bottleneck of civilization dissolves. Colonies on Mars no longer count kilowatt hours like ration coupons. Engines can burn ion propellant with abandon. Water can be split into oxygen and hydrogen for air and fuel, not grudgingly but generously. Even the dream of terraforming the warming of frozen worlds with redirected sunlight slides from fantasy toward practicality. Some see this as the inevitable trajectory of growth, others as hubris, the same appetite that drove us to strip our own planet now writ across the solar system. But whether we frame it as ambition or sin, the logic circles back. If humanity survives long enough, our energy demand will push us outward. Fossil fuels will be dust. Nuclear fission, a stopgap. Even fusion, should we master it, draws its input from the same star. Eventually, we either learn to mine our sun directly, or we stagnate. Perhaps Mercury will endure, untouched, a relic we decide is too sacred to carve. Perhaps asteroids and comets will be enough, their combined bulk melted and flung into orbit to build the lattice of collectors. But the principle remains. The solar system holds more mass than we could ever use, and more sunlight than we could ever burn. To think at the scale of a Dyson swarm is to admit that humanity's boundary is not Earth, not even Mars, but the sun itself. In that realization lies a quiet shift. Colonization stops being about single rockets carrying fragile pioneers. It becomes about industry persistent, replicating, automated industry that reshapes worlds not with flags and footprints, but with furnaces and forges. The frontier becomes less about the courage of astronauts and more about the coordination of machines. If this feels colder, it is also more honest. Civilization is not carried outward only on shoulders. It is built outward by hands of steel and silicon. And so the image endures. A dark star, glittering with human mirrors, the light of the sun refracted into purpose. The cost is a planet. The reward is a future where power is no longer a ceiling but a floor. Beyond that floor waits the true challenge, what we will do with the abundance we've claimed, and what kind of people we will become in the shadow of a harvested Sunday. But before we can step into that abundance, we must confront another limit, not of machines or planets, but of ourselves. For beyond Earth's shield, a silent enemy waits, written in radiation and time. Every technology for propulsion, every dream of Dyson swarms, bends finally back to the same fragile anchor, us. Ships may hum for decades, mirrors may drink the sun, but the cargo that matters most is human life, soft, fallible, mutable. And outside the cocoon of Earth, life is under siege. Our planet is wrapped in a magnetic cloak, an invisible shield spun by its molten core. It deflects solar wind, bends cosmic rays, and blunts the background storm of high-energy particles that cross the galaxy. Within that shield, the radiation dose we absorb is trivial, 3 millisieverts a year, the equivalent of a few chest X-rays spread over 12 months. Our DNA, our cells, our tissues, can absorb the blows and repair themselves. We flourish. Step beyond that shield, and the storm begins. On the moon, where no magnetosphere softens the sun's fury, radiation levels spike 200-fold. Standing on that grey dust, an astronaut receives in a single day the dose that Earth would deliver in months. Travel further into interplanetary space, and the numbers grow cruel. A round trip to Mars, even with shielding, could tally 1,200 millisieverts already past NASA's lifetime exposure cap for astronauts. One voyage, and your career in space is over. Europa, the icy moon of Jupiter, is worse. There, within the giant planet's trapped radiation belts, you would accumulate 5,500 millisieverts in a single day. At that dosage, survival odds collapse. A 50% chance of death within a month. Radiation is not an abstraction. It is a predator, silent and invisible, written in mutations, cancers, and sterility. It slices through DNA like a vandal through pages, leaving errors behind that multiply with every division of every cell. For explorers, this is not merely an occupational hazard. It is an existential war. To settle Mars, to live in space stations, to mine asteroids, we must endure the storm. And so, engineers pile regolith atop proposed Martian habitats, stack water barrels around spacecraft cabins, dream of superconducting coils that bend radiation aside like Earth's own field. Shielding is mass, and mass is expensive to lift, but survival demands it. Even with shielding, the long durations of spaceflight grind at the body. Gravity, which has always been our silent partner, vanishes. Bones leach calcium into blood, muscles atrophy without resistance. Astronauts aboard the International Space Station lose strength despite hours of daily exercise. Their faces puff with blood, their eyes warp from pressure shifts, their arteries thicken. Even their very genes alter expression, as NASA's twin study revealed. 6 months in orbit, and one brother's DNA diverged from the other's. Telomeres shortened, immune systems weakened. Most changes faded after return to Earth. Some did not. Time itself becomes an adversary. Space does not forgive boredom, isolation, or the sheer scale of waiting. 7 months to Mars means 7 months confined with 100 souls in a tin can. Every argument amplified, every silence louder than gravity. Psychology becomes engineering. and engineers must learn to design not just systems, but societies in miniature. And yet, beyond these practical hurdles lies a deeper urgency. The sun, our parent star, is on a clock. In 6 billion years, it will swell into a red giant, swallowing Mercury, Venus, Earth. Every forest, every archive, every poem will burn. That timescale is almost incomprehensible, but we do not need billions of years to feel the risk. A stray asteroid, one large enough to repeat the dinosaur extinction, is statistically overdue. Cosmic dice are always rolling, and Earth, for all its beauty, is a single point of failure. To survive, we must scatter. Colonies on Mars, bases in the asteroid belt, cities in domes under Europa's ice, each would be a safeguard, a way to spread risk across worlds. Evolution did not design us for this, but survival may demand it. Which brings us to the quiet revolution already underway, one as controversial as it is powerful, altering ourselves. For if shielding can only do so much, if psychology bends under confinement, if radiation writes mutations faster than our bodies can erase them, then perhaps the answer is not only to protect humans, but to change what humans are. Gene editing, once the realm of science fiction, is now in laboratories, tested even aboard the International Space Station. With CRISPR, the molecular scalpel, scientists have cut and replaced sequences of DNA in yeast, repairing radiation damage in orbit. The step from yeast to astronaut is vast, but the principle is clear. Biology itself can be engineered into resilience, and that realization cracks open an even stranger future. What if the solution to radiation is not thicker walls but thicker skin, written into our genome? What if survival in Europa's storm belts requires borrowing from creatures more resilient than us? The water bear, the tardigrade, produces a protein that shields DNA from damage. Transplant that gene into human cells, and resistance rises by 40%. Already tested, already achieved, if only in dishes of tissue under microscopes. The line between possible and practical grows thinner with every year. This is where the frontier bends from steel and stone back into flesh. To colonize the solar system is not only to ask how we build rockets or mine planets, it is to ask how much we are willing to change ourselves to survive the voyage. And once we open that door, it may never close. In 2021, aboard the International Space Station, NASA ran an experiment that barely made headlines. Yeast cells had their DNA sliced, a segment removed, and a healthy piece stitched in its place. To most, it was a technical demonstration. To historians of the future, it may read as the first footnote in a new chapter of humanity, the moment we began to edit ourselves, not in theory, but in orbit. CRISPR is the scalpel of this new medicine, an elegant system borrowed from bacteria that snip and paste genetic code with astonishing precision. On Earth, its promise is already vast, correcting mutations that cause diseases like sickle, cell anemia, removing the genetic seeds of blindness, reshaping the destiny written in chromosomes. In space, its potential is starker. Radiation does not just wound cells, it corrupts their blueprints. DNA strands snap, bases mispair, sequences go missing. Shielding can slow this, but never stop it. Repair must happen at the genetic level, or not at all. The simplest application is maintenance, trimming away damaged DNA and replacing it with healthy sequences, like patching the tread on a worn tire. Already this would extend an astronaut's career, counteracting the steady toll of cosmic rays, but CRISPR does not stop at repair. It can add, it can borrow, it can reinvent. Consider the tardigrade, the humble water bear, so tiny you need a microscope to greet it. These creatures shrug off radiation, desiccation, even the vacuum of space. They owe much of this resilience to proteins like DSUP, which wrap around DNA like blankets, shielding it from harm. In 2015, scientists transplanted the DSUP gene into human cells. Those cells became 40% more resistant to radiation, 40% enough to transform a lethal voyage into a survivable one. A modest edit, a single borrowed gene, and biology itself leans toward the stars. It is easy to imagine the next steps. Genes for better hemoglobin to thrive in thin atmospheres. Genes from extremophile bacteria to endure cold or heat. Proteins to scavenge free radicals more efficiently, slowing the mutations that age us. CRISPR, refined and extended, could become not just a medical tool but a colonization kit, a library of adaptations, each waiting to be stitched into the genome of those bound for hostile worlds. But biology is rarely neat. Genes do not act in isolation. Each is a switch connected to circuits we barely understand. Edit 1, and you may change more than you intend. The one gene, one trait dream dissolves on contact with reality. Traits emerge from constellations of genes, from layers of regulation, from networks we are only beginning to map. To add DSUP might protect against radiation but alter cell division in subtle ways. To borrow antifreeze proteins from Arctic fish might help in cold, but what if it alters kidney function or immune response? Even so, the momentum of discovery is forward. CRISPR trials in humans have already reached the clinic. In 2018, a Chinese doctor announced the birth of twin girls, Lulu and Nana, whose genomes had been edited before birth to resist HIV. The work was reckless, secret, condemned, and the scientist jailed. But the fact remains, the first edited humans are already walking among us. The genie is not returning to its bottle. This raises the harder question, not of what we can do, but what we should. Repairing radiation damage seems pragmatic, even merciful. Curing genetic disease is already celebrated. But where is the line between therapy and enhancement? If a Martian colony requires radiation resistance, is it ethical or mandatory for every settler to receive edits? Would a child born on Mars without the right genes be condemned to sickness or excluded from society? Would genetic modification become a passport, a license to leave Earth? And what of inequality? At first, these technologies will be expensive, gated by wealth and access. Enhanced humans able to withstand radiation, metabolize food more efficiently, resist cancers may diverge from their unmodified peers not only in biology but in opportunity. Space could become not merely a frontier, but a filter, one where the edited rise and the unedited remain planet-bound. Yet the arc of technology bends toward ubiquity. 1,000 years from now, edits that seem extraordinary today may be as common as vaccines, available to all, taught in schools. Gene editing could become less a medical procedure than a form of self-expression. Traits could be selected, tuned, even swapped. Eye color today, resistance to toxins tomorrow, immunity to solar storms next summer. Some scientists, like Christopher Mason, imagine futures where humans can toggle genes on and off at will, customizing themselves as casually as changing clothes. Such visions blur the definition of human. If our genome becomes a canvas, if our bodies are reworked with borrowed or invented genes, what remains of our shared identity? Is humanity defined by DNA, by form, by culture, by continuity? If colonists on Titan adapt themselves with antifreeze proteins, if European settlers grow radiation shields in their cells, if Martians sprout traits unknown on Earth, are they still us, or something new? The philosopher might recoil, the engineer might shrug, for the vacuum does not care what counts as human. It only asks, can you survive here? If not, you must change. If yes, the cost is yours to weigh. And so, as propulsion evolves to carry us further, biology will evolve, or be evolved to endure the journey. Rockets may open the path, but only through editing ourselves may we be able to walk it. And if we take that step, the solar system may no longer be inhabited by a single human species, but by many. Imagine walking through a Martian colony 1,000 years from now. At first glance, you might think you are still among humans, 2 legs, 2 arms, faces familiar in outline, but then you notice the subtle differences. Taller frames, bred or edited to take advantage of low gravity, eyes that gleam in the dim light, widened or enhanced for twilight vision. Skin that carries a faint sheen, thickened or altered to shield against radiation. These are not aliens, they are us. Yet they are no longer the humans who first left Earth. Adaptation has always been our story. When ice gripped Europe, our ancestors grew hardier. When deserts expanded, our cultures shifted to endure the heat. But genetic editing accelerates this old process, condensing millennia of natural selection into deliberate design. In space, the possibilities explode. A colony on Pluto, wrapped in eternal dusk, might develop or engineer low-light sight, or even echolocation borrowed from bats. On Europa, settlers beneath the ice could weave genes for antifreeze proteins into their cells, their blood refusing to freeze even in extremes. In underwater habitats, humans might one day breathe with gills, their lungs modified with strands of DNA from fish or amphibians, opening Earth's oceans as new homes while preparing us for aquatic exoplanets. Even more radical futures beckon. Long voyages between stars, even with improved propulsion, may still stretch across decades or centuries. To survive them, humans might re-engineer metabolism itself. Some might hibernate, borrowing the tricks of bears or squirrels. Others might adopt chloroplasts, embedding plant-like organelles into their skin to supplement meals with photosynthesis, basking under artificial suns inside starships. Some may learn to thrive on unusual diets, bacteria that digest plastics, worms that metabolize metals traits spliced into us to expand our menu in leaner worlds. And senses could multiply beyond today's imagination. Imagine workers with the ability to perceive radiation directly, their eyes tuned to X-rays or ultraviolet so they can spot danger before a storm strikes. Others might sense electromagnetic fields as sharks do, feeling currents hum around them. Soldiers or explorers might toggle enhancements on and off a heat vision mode for night patrol, a high oxygen metabolism for strenuous climbs, all governed by genes switched like software. The practical advantages are obvious. A Titan settler resistant to cold won't need endless layers of insulation. A Martian colonist resistant to radiation won't fear every solar flare. A deep space traveler who eats sparingly or photosynthesizes lightly won't drain precious ship stores. But with practicality comes culture, and with culture comes division. For how long would we still call all these forms human? A person with gills, glowing eyes, and radiation. Proof DNA. Does Earth see them as kin or as other? What happens when entire generations grow up edited for their environments, until the differences are not just cosmetic, but fundamental? Over centuries, new branches of humanity could diverge so far that interbreeding becomes impossible. Speciation, a process that once took geological time, could happen in centuries under the scalpel of CRISPR. The social consequences are as profound as the biological. Will edited humans see themselves as superior? Will baseline humans resist, fearing irrelevance? Will children be pressured, even required, to accept edits before joining off-world colonies? The old debates about inequality may return with sharper edges, written in genes rather than wealth. And yet, diversity has always been our strength. Just as cities thrive on many cultures, perhaps the solar system will thrive on many human forms. Mars-born engineers, stockier and radiation-hardened, may work side by side with Titan explorers built for the cold. Jovian settlers, bred to handle intense radiation, might trade with aquatic colonists on Europa. Over time, these differences may create new myths, new identities, new nations each proud of its heritage, each uniquely adapted to its world. Even Earth would change. Gene editing will not remain confined to space. Already, designer traits are conceivable. Sharper eyesight, stronger immunity, enhanced intelligence, extended lifespans. Some will choose wings for fashion, tails for utility, or skin patterns for beauty. The line between medicine and artistry will blur until DNA becomes a canvas as malleable as paint. What begins as survival may end as self-expression. But abundance brings peril. If humanity fragments too far, communication and empathy may falter. 1,000 years hence, a meeting of Martian, European and Terran delegates might feel less like family reunion and more like diplomacy between species. What will hold us together then? Shared history? Shared language? Or the knowledge that all our edits, all our adaptations, trace back to a single fragile planet, a blue cradle under the sun? Propulsion may scatter us. Dyson swarms may feed us. But it is gene editing that will define us, reshaping not only how we live, but what we are. To colonize the solar system is to accept that human is not a fixed state, but a spectrum, one that may expand until we look at one another and see not just difference, but new forms of kinship. And if that spectrum grows, if the solar system fills with voices speaking from bodies we no longer fully recognize, then another question looms: how will we remain connected across distance and difference when the gulf is not just physical but human? For all our dreams of ships and colonies, of edited humans and Dyson swarms, one truth persists. Distance does not only separate bodies, it separates voices. A civilization scattered across the solar system must talk to itself, or else it is no civilization at all. Yet communication, as much as propulsion, is bound by physics, and our current methods are already straining under the silence of space. We speak to our machines with radio, the same spectrum that carries FM music and cell phone chatter. The principle is simple, but the scale is not. Voyager 1, still whispering from interstellar space, does so with a transmitter no more powerful than a refrigerator light bulb. Its voice, faint beyond imagining, spreads outward until it brushes Earth's network of colossal dishes, the deep space network. These antennas, 70 meters wide, are humanity's ears in the void. With them, we captured Neil Armstrong's first words on the moon, steadied Apollo 13 when its oxygen tank exploded, and listened to data trickle back from New Horizons as it glanced at Pluto. But the void is vast, and radio is slow. Bandwidth, the amount of information that can cross the gulf, collapses with distance. New Horizons at Pluto needed 2 years to send home its photographs and readings, 2 years to download what your phone might fetch in minutes. Missions plan around this bottleneck, compressing images, rationing data, choosing which treasures to keep and which to discard. Every byte is precious, every command delayed. As we push further, the gap will only widen. The deep space network itself groans under the load. 3 sites in California, Spain and Australia divide the sky, handing off signals as Earth rotates. Each antenna can listen to multiple spacecraft, but can speak to only one at a time. Their age shows, repairs take months, and the 70-meter giants are nearing retirement. Yet the demand grows. Rovers on Mars, probes around asteroids, orbiters studying the gas giants. A constellation of ears, but not enough voices. NASA's answer is light. In 2021, it launched the Laser Communications Relay Demonstration, LCRD, a satellite in geosynchronous orbit that sends information not by radio but by infrared laser. The difference is dramatic. Light waves are far shorter than radio waves, so they can carry far more data. Where radio offers kilobits, optical systems offer gigabits. It is the leap from dial-up to fiber optic. Imagine rovers streaming high-definition video from Mars instead of compressed stills, or astronauts in lunar orbit making video calls home, with no delay in clarity. But lasers demand precision. A radio dish can afford to be sloppy. Its beam spreads, and the Earth can catch the signal even if it wobbles. A laser is a needle, narrow and sharp. Spacecraft must aim with uncanny accuracy, keeping the beam locked on Earth across millions of kilometers. And Earth is fickle. Clouds scatter light, storms block the path. To counter this, NASA builds ground stations in places like California and Hawaii, where skies are often clear, and plans networks flexible enough to reroute around weather. Already, future missions prepare to test the leap. Artemis 2 will carry astronauts around the moon and beam their journey home in ultra-high definition. Psyche, launching to a metal asteroid in 2026, will carry the deep space optical communications payload, testing laser links across 240 million kilometers. If it succeeds, the solar system may begin to glitter with beams of light invisible to our eyes, but binding planets and ships together in a web as fast and rich as anything on Earth. This is more than convenience. It is survival. Colonies cannot thrive if they are mute. Science cannot advance if its data takes years to return. And culture, our songs, our arguments, our laughter, cannot endure if distance means silence. High bandwidth communication makes the difference between lonely outposts and a living network, between a scattered species and a single civilization. Imagine a future Mars base, not just exchanging short bursts of telemetry, but holding live classrooms with Earth, children learning across planets. Imagine asteroid miners uploading terabytes of scans to a central library, their work instantly folded into shared knowledge. Imagine ships on their way to the outer moons streaming their journey in real time, so that no voyage feels isolated. The challenge, as always, is to scale. Lasers work in principle. The engineering is difficult but tractable. The question is whether we will build the infrastructure. Fleets of relay satellites, networks of optical ground stations, swarms of antennas still humming in radio for redundancy. Communication is not a single experiment. It is a system, sprawling and resilient, that must grow as fast as our ambitions. If propulsion lets us move, and power lets us build, then communication lets us remain whole. Without it, we risk becoming strangers to ourselves, colonies drifting into silence. With it, we can stitch the solar system into something like a society, an archipelago bound, not by oceans but by light. One day, perhaps, our descendants will look back at the faint radio whispers of Voyager and smile. They will see them not as relics of primitive technology, but as the first proof that voices could cross the gulf. From those whispers came lasers. From lasers, a lattice of light, and from that lattice, a civilization that speaks across worlds. And in the end, that may be the greatest invention of all. Not the engines that carry us, not the swarms that power us, not even the genes that reshape us, but the simple ability to call across the dark and know someone answers.